Welcome, everyone. I propose we start with today's Water Institute WaterTalk. It's my pleasure to introduce to you Prabhakar Clement, who's going to talk today about complexities in groundwater models. As you can see, he's a full professor in the Department of Civil Engineering at Auburn University, where he currently holds a distinguished title position, the Harold Vince Groome Endowed Scholar in the field of environmental engineering. Dr. Clement joined Auburn University as an associate professor in 2002 and became a full professor in 2007. And he was awarded the Arthur Vegan Research Chair Professorship in Auburn in 2007, which he occupied until 2012. In 2013, the American Society of Civil Engineers elected him to the rank of ASC Fellow, and in that same year, the Peking University awarded him the Globex Fellow. Before joining Auburn University, he was a tenure-track faculty member in the Department of Environmental Engineering, the Center of Water Research in Perth in Australia, and was a postdoctoral fellow and then a senior research engineer at the Battelle Pacific Northwest National Laboratory in Washington from 1994 to 1999. And so today he's going to talk about complexities in groundwater modeling. The floor is yours.
Thank you. First of all, thanks for inviting me. I wanted to visit Waterloo. I've been trying to do it for almost 2 years now. I do not want to give away this opportunity because by this time next year, we will have a wall across Mexico. Trump will be our president, and then every American is going to rush to Canada, and you guys are going to build a wall here. So it's a buy one, get one deal, right? So I thought, and Canada will pay for it, actually. So I thought before that happens, I should escape to Canada and give my talk. So thanks to James Craig for inviting me, and we've been in touch for a long time. And it's an honor to visit this department because I obviously, as a graduate student, used MLFriend and all the work which came out of this program. So it's my first trip to Waterloo, so thanks for that. Okay. So what I'm going to talk about today is, I know it's the groundwater audience have done a lot of work, so this is more of a philosophical talk. So in order to kind of set this talk up, so let me first acknowledge this is really not, the ideas I'm going to talk are completely not mine. By random choice, I got selected to serve on a National Academy panel in Washington, D.C. to look at a problem. And if you look at the list, these are incredibly distinguished lists. The guy who chaired this, David Sivitz, who is a vice provost of Brown University, is a National Academy member. Somehow randomly, I ended up on this thing. So this is kind of a sharing how groundwater is viewed from outside. And I was the only groundwater hydrologist in this panel, which has medical professionals. And so here's an application of groundwater model and how it's viewed from outside. So I thought I'll just share it with you. So I need to credit all these guys, and the details are all in a National Academy report. It's like a 300-page large report. So if you want to read more on it, you can look at it. Now, in order to set up this problem, so let me highlight a little exchange which happened between Jon Stewart and Elizabeth Warren, potential presidential candidate, used to be at least, now a senator actually. This was in 2009. The US economy is just falling apart. And they had created this TARP, which is a program to stimulate economy. And the Elizabeth Warren was running it, and she came to the Jon Stewart show, and I love Jon Stewart. I miss him, actually. So it's a nice political satire show. So she came there, and they started discussing about this program. So as a part of the discussion, and I was doing this project at the same time, so at a part of the discussion, Stewart asked this question: how do you stress test a bank? They want to decide which bank will survive. So they said, we're going to do a stress test of a bank. I said, that's like slug test. That's like pump test. So that immediately caught my attention. So I said, what is this? And then Warren said, well, you basically run it through a bunch of mathematical models, and you figure out then whether you think the bank will financially healthy or not. Just think about it a little bit. Bank is such a complex problem, right? So they're going to run through a model, and the bank, you'll say, oh yeah, Wells Fargo, great. SunTrust Bank, bad. And when she said that, I said, how could he use a mathematical model to make such an important decision, right? And I thought Stewart would just completely go after her for making a statement like that. But what he said was, immediately Stewart said, oh, really? OK, great. So you have a rational approach then. And then completely backed off. Okay? So essentially what Warren claimed is there is a magic mathematical model which can solve such a complex economic problem, and nobody challenged, basically. Okay? Now, for those of you who use mathematical model, you will start scratching your head. Okay? And probably you might be saying, oh no, these economics always come up with crazy stuff, right? And we are geologists or civil engineers. We will never do that. Okay? We will never do that. So I'm going to make a claim. We sometimes do that. Okay? And so here's that's how the case study starts. Okay? So let me show a quick video so you know the background on this.
Tonight, we're bringing you an important investigation. An extraordinary group of men, some of whom defended this country, have developed a very rare disease. And all the men have a common link in their past. They fear it may be something in their common history that caused their illness. And Abby Boudreau of our Special Investigations Unit sat down with them.
These men are all victims of a terrible disease. A disease especially rare among males. They have breast cancer.
I never at that time knew that men could even have breast cancer until I was told by the doctor, and I was like, that's when I was shocked, like, you got to be kidding me.
But beyond their rare illness, these men share another link. They're all retired U.S. Marines or children of Marines. And years ago, they lived on the same Marine base.
We come from all walks of life. Some of us have college, some of us blue-collar jobs. We're all over the country. You know, we're not. What is our commonality? Our commonality is that we all, at some point in our lives, drank the water at Camp Lejeune.
Camp Lejeune is the main U.S. Marine Corps training base in North Carolina.
How many of you believe that your breast cancer may be tied to the water at Camp Lejeune? All of you.
They've each had part of their chests removed by surgery. All suffered through brutal chemotherapy or radiation, or both. Some were told their cancer was terminal. These are just 7 of at least 20 former Marines or sons of Marines with breast cancer who lived at Camp Lejeune.
Mine traveled to my spine, my ribs, and my hip.
Peter Devereaux is 47 years old. He was diagnosed with breast cancer last year. He was at Camp Lejeune in 1981 and 82.
The difference with metastatic breast cancer means now there's no cure. So the average life expectancy is 2 to 3 years. So, you know, I have a daughter at home, 11 years old, you know, and you're in this thing and, and it like pisses you off, right? Being a man, you know, I try to take care of my wife and my daughter, and now that I'm considered disabled because I can no longer work, I can't use my arms, you know, you're having challenges, you know.
Jim Fontella from Detroit fought in Vietnam and lived at Lejeune in 1966 and 1967. He was diagnosed with breast cancer in 1998. After surgery, it reoccurred, spreading to his spine and back.
I kind of manned up to it after a while and just expected to die, because once you have metastasis, bone mets, basically it's just a matter of time before you die. You know, luckily I've already passed my due date by 5 years. I've outlived that death sentence that I got.
Mike Partain, the son and grandson of Marines, was born on Camp Lejeune 40 years ago.
When am I going to see my daughters graduate? I'm sorry. When they told me they had breast cancer and that it was serious, I mean, the first thing in my mind was, am I going to see my kids graduate from high school? Am I going to see my daughters married?
Partain has helped find and organize these men. Like most of them, Partain has no family history of breast cancer. He even got himself tested for the breast cancer gene.
And they were negative.
Breast cancer in men is far more rare than in women, with only 1,900 men expected to be diagnosed in the U.S. this year, as compared with about 200,000 women. Dr. John Kylick is a breast cancer surgeon at Moffitt Cancer Center in Tampa, Florida. He's startled by the common threads.
Do you think that this raises any red flags?
Absolutely. When you have the average breast cancer patient for males is about 70 years old. So when you have gentlemen that are in their 30s stepping forward without a family history of breast cancer, that is alarming. And the question is why? Why is this happening to them?
Frank Beauvais, with the Federal Agency for Toxic Substances and Disease Registry, has been working to answer that question. He says the levels of contamination at Camp Lejeune were alarmingly high.
The levels of trichloroethylene were the highest I've ever seen in a public water system in this country.
Government records show from the 1950s through the mid-1980s, Camp Lejeune's drinking water was contaminated with high levels of chemicals and solvents. Some came from a nearby dry cleaner. Others were chemicals used on the base. The contaminants included trichloroethylene, or TCE, perchloroethylene, or PCE, and benzene, all believed to cause cancer.
Now, whether the exposures were long enough and high enough at Camp Lejeune to cause disease, that's the question.
The Marine Corps declined to be interviewed for this story, but said in a statement that it addressed the contamination as quickly as it was discovered, and that it has collaborated with the Toxic Disease Registry from the beginning of its studies to determine the extent of the contamination and whether adverse health effects may have resulted from it. This collaboration continues to the present day. For these men, collaboration isn't enough. They want answers, and they say they want help.
To have 20 men come from the same place, walking on the same dirt, drinking the same water. I mean, there has to be a link there somehow.
But so far, no link has been proven. And the Veterans Administration says without that link, it cannot pay for treatment. For these men, it's a bitter disappointment that leaves them angry.
Why anger?
Well, anger because the Marine Corps did this to me. How could they do this to me, after I've served the country faithfully, honorably discharged? How could they do this to my fellow Marines?
And Abby Boudreau is here with me now. Abby, why is it so difficult for scientists to find a link here?
Right, well, first of all, you have to realize that this base is huge. It's 150,000 acres. And then you have to go back 20 or 30 years to try to piece this puzzle together. I mean, where exactly did these men live? You know, what kind of water were they drinking? Was the water contaminated? These are all the kinds of questions that scientists are going to ask and have to ask in order to find out the truth here. And that's what needs to happen in this case, and it needs to happen soon.
How seriously is it being taken, really?
It is being taken very seriously. Every single scientist and research that we talked to was alarmed. They said this is startling. They haven't seen something like this. You know, you have 20-some men who all have male breast cancer, who all lived at Camp Lejeune, who were young when they were diagnosed, who most of them don't have family histories. So this is a big deal, and these men just want to know, was it because I lived there? Was it because I drank this water? And it might take a very, very long time to find that out.
So let me summarize that video you just watched. Basically, the groundwater issues are groundwater at the Camp Lejeune was contaminated with several organic contaminants, including PCE, TCE, and benzene, actually. And there are several other mixed waste disposed at this site. This was not the only contamination problem. And it's a fact that several former Camp Lejeune residents have reported various health issues. Breast cancer is one of them, but there are other cancer issues and other incidences. The question is, did the contamination cause? Is there a causation? If so, how do we compensate them? How do we pay their medical bills? And that was a contentious issue. Okay. So what happened was, when this became a contentious issue, they put out a tender to bring in some modelers to tell this thing. So here's what the modeling team. Well, before we do that, and the modeling team put together a model, and we were brought in by the National Academy to evaluate, hey, how much we should study this problem to actually make a resolution. So the National Academy asked the committee to say that we will review the scientific evidence on the association between the adverse health effects and the contamination, and advise the Congress, basically, what kind of a bill should be drafted and who should be compensated and who should not. And they were very truthful about it. I mean, it's amazing. We had a 3-star general, Eugene Pine, who recently retired. This guy had like command to take off a country, send a big aircraft and bomb the entire country. And he would sit with a bunch of scientists and said, use your science to tell us what happened. Predict the past. You are the only hope we have. And he was very honest about it, okay? And so with the same interest, they also funded several projects, and one of the major initiatives they did was funding a mathematical modeling project at the site. Now, when we talk about models, at least in a groundwater sense, there are two types of models. One is epistemic model, right? We basically, in a typical epistemic model, you generate hypotheses and you test them, actually. And models are great for that. I mean, you just generate something and test it. The second type of models are mostly policy models, okay? Now, policy models can be used in two ways. One is forecasting models. The global warming is a good policy model where you forecast a global climate change and make some action. And the second one is called hindcasting model. You run the model backward to find what happened in the past and to make some policy decision. And this particular talk is very restricted to hindcasting model. Whatever comments I make, I want to make sure you understand that I'm talking about a hindcasting model, because they're very unique, actually, because they are talking about the past which is gone. There is no data possible now, okay? Now, when the proponent of this modeling project, when they wrote the proposal, this is what they said, and that was posted on the website. And their website said, water modeling, which means groundwater modeling, is a scientific method that will help estimate past water system conditions that no longer exist today. Using water modeling methods, we will help the scientists to fill the missing data, okay? And these models will tell us the past, okay? So I put this little cartoon. All they are saying is there's a little magic wand where they can actually ask this question, right? Tell me what happened in the past, and this is going to reveal it to you, okay? So that's how they actually wrote the proposal, and they actually got funded. And then they did their work, and they used a fairly complicated model, and I got my own model. The way in which I got into this project was I have a fairly complicated model called RT3D. It's a reactive transport model which runs with ModFlow. They use some components of these things for do the prediction. So that's how and we can put all kinds of complexity in a numerical model. Okay? So they did their work for 3 years, and then they actually went under oath to Congress and testified. Their group leader testified on April 27th. The project leader stated, effective today, former Camp Lejeune Marines and their families can find their estimated exposure level to PCE and PCE biodegradation products calculated through modeling by visiting our website. So they actually made some prediction, and they created the website and then put the numbers out, okay? Now, if you think from a point of view of Camp Lejeune folks, if you saw the video, they said, well, we want to know what happened, right? So you go to the website, it'll tell you what happened, actually. So the modeling did a fantastic job. So I said, okay, let me go to the website and check it out. So if you went to the website, so I picked some numbers because I was born in '63. Let's say, for argument's sake, I was in Camp Lejeune, I got this number. How I would feel is, well, I can see, well, when I was born, I'm probably exposed to 58.81 PCE, 2.55 TC. This is actual website. And when I was 10 years old, I was 42.25. When I was a teenager, I was cranky because I was probably exposed to higher doses, right? So it gives you a causation. As a common man, when you see this, it really helps, actually. So when I actually looked at his number, I mean, this was the time Obama just got elected, so we were all like very happy, right? So I had this little smiley face saying that, oh yeah, it's great. I mean, as a modeler, we are accomplishing a lot. So I put this little smiley face there, okay? And then they also provided this long-term forecasting, which basically said the contamination kind of broke through around within 2 years and then became kind of stable, and they did some uncertainty analysis, and these are the uncertainty bounds. Now keep in mind, until this point, there is absolutely no data. When the data showed up, somehow model did some cranky stuff, actually. We're going to look at it carefully, okay? But in general, when the data is not there, models did a fantastic job, okay? And that's what we are interested, okay? That's what people are interested at that time, okay? So again, it's great, small uncertainty bound, okay? Now here are actual reactions. As I said, I was the only groundwater hydrologist. There was a civil engineer who was a water supply engineer in the team. The rest are all medical doctors from Harvard, Yale, all these epidemiologists, all kinds of experts. These are the actual statements. The engineers have completed a fantastic modeling effort for the site. We now know the exposure concentration levels, and we can proceed with health risk assessment and epidemiology studies, okay? So they put incredible amount of faith in us. The residents felt that we now know how bad the poisoned water was, okay? And we can now know why it happened. So the causation is kind of, they're very happy about it. Again, as a groundwater hydrologist, I thought, you know what, we're doing a fantastic job. So I kind of patted on my own back, actually. So things were going well. Now, on one of these days, on my day of reflection, I said, wait a minute, okay, now on my research side, I hate heterogeneities. I work on homogeneous isotropic glass beads, not even sand. I can't even tolerate sand heterogeneities, okay? So a guy like this, I said, wait a minute, I mean, can we really do such a good job in such a complicated problem? If I have to be honest to myself, should I be sad or happy? I don't know that, okay? Now, at the same time, I also opened the latest WRR issue, actually. This was a 2009 Brian Berkowicz's paper, okay? Now, let me give a background a little bit on Brian. Brian Berkowitz was the editor of WRR at that time, and he works in Israel with Technion, and he's one of the leading scientists, actually, okay? And he wrote this paper, actually. And the problem he considered was, he took a one-dimensional column, basically, and packed half the column with fine glass beads. He also likes glass beads. And the other half, he put coarse glass beads, okay? Now, if you do a theoretical calculation on a spherical glass beads and if you uniformly packed, theoretical porosity is roughly about 42 to 45%. So the porosity doesn't change. It's not a function of particle size, okay? So the system has got uniform porosity, okay? One side is fine, one side is coarse. So what he did was then, he took this column, and we actually repeated the experiment, so maybe I'll show the experiment. You can see that we repeated. So the right-hand side is a fine glass bead, left-hand side is a coarse glass bead. The porosity is roughly the same because it's a spherical glass bead, uniform glass beads. And what you do is you send a non-adsorbing chloride pulse from the left and look at the breakthrough in the right, and then you switch it around. What you do is just literally switch it around. Take the pump here, put the sampler there, and look at the breakthrough curves, okay? Now, the theory would tell you it will be identical because the porosity is same, V is same, so if you look at the advection diffusion equation, you should get a similar breakthrough. So he actually ran this experiment. So that's the equation we use, which is a simple one-dimensional advection dispersion equation, nothing magic about it. One is a convection term, which moves things. Other is a diffusion term, which mixes things, and I call it as a confusion equation, actually. Because the velocity is usually a convection term. We really don't know about it, but somebody tells us what it is. And diffusion is a confusion term, actually. We really don't know anything about it, so we just throw it in there, okay? Anyway, but does it work for the system? Well, the black balls and the white balls are from left to right and right to left. You got a great breakthrough curve, almost identical, okay? There are a little bit of this thing. So I looked at it, oh yeah, great, yes we can, right? It worked fine. Now, then what he did was, he was running the column at 1 ml per minute, and then he slowed it down. As he starts slowing it down, there is some sort of a chromatographic separation. In fact, it's a very interesting paper, which kind of falls apart, actually, okay? The theory would say it will come, and it completely falls apart. As it starts slowing down further, it starts separating, okay? And now there are a series of papers written why it happens. It's all the interface problem. And when it comes to the interface, there are several theories, okay? So there are a series of papers written, so I don't want to go through that. But the thing I wanted to convey is the period when we modelists are so successful predicting the past that the top scientists cannot predict salt moving through a half a meter column filled with glass beads, okay? So the state of the art, WRR, is we can't even know how to predict a salt movement in a glass bead column. But the application side, we are predicting the past using this nice complicated program. I thought there is a problem there, okay? Now, then you sort of carefully look at the field model. A typical field is not a glass bead field. I mean, it's got all kind of heterogeneities, right? And then we don't even know the bottom of the aquifer because we can't drill there. So it's most of the boreholes at that site stopped way above the so-called confined layer. And then the source itself is the DNAPL source, which means it's a non-aqueous phase liquid, so it doesn't dissolve in water, and then it sinks. I mean, you can't get better than that, actually, okay? And so it goes everywhere, oozes out. It's a DNAPL source. And then they were talking about some other, their biological model used microbiology. Well, that's a complicated problem. You need an electron acceptor, and then you need a special kind of bacteria called Staphylococcus. And there is a whole lecture can be given on how reductive dechlorination happen in PCE. Highly complicated pathway. Now, how do they do this? Well, they simplify this, basically. They simple layered model, and then you always cite the Gellhardt's paper. Okay, yeah, we found the dispersion from Gellhardt's paper. That's a WRF paper, so it should be right? And then you throw some decay coefficient. That's exactly what they did. And they predicted this thing, okay? But what you can see is in this prediction, the minute they had some data, they had some trouble, okay? So if you had a very close look at it, so here's a source. This is a 1 kilometer by 1 kilometer grid here I'm showing. Where's my, okay. So that's a source. There was a well right next to it, actually, immediately sucking. If you look at the breakthrough curve predicted by them, the actual data, they had very few data. So the actual data varied from, 1,500 microgram per liter to all the way to zero, almost zero, actually. And the curve went somewhere in the middle. I could have drawn the curve anywhere I want, actually, literally, right? But when you look at this big scale, it doesn't make a difference, actually. It looks as if you predicted the average. So that's the kind of data you predicted. So it's a complete approximation, just an average information. So the question then is, why is it happening? Why the real models fail this badly? That's because it's nothing wrong about modelers. It's not that models are incompetent, but the problem is there are inherent uncertainties in a complex groundwater problem like this. We are dealing with an open system, which means that it rains and shines, and we don't know. We have no control on all these stresses. Past external stresses are difficult to quantify. We don't know how much pumping was happening. They all approximated, okay? We have very little knowledge about the source. That's a very important point, because when people created some of these sources, they never thought, well, WaterTalk guys will come and model this. So we got to make a good record. Okay, I'm going to throw 10 grams of DNAPL, put it in. So because one day, Dr. Craig will come and ask us, okay, so we got to give it to him for his model. No, they just dumped it, actually, right? It's a dump site. And very little knowledge about biogeochemistry. We are still learning. I mean, D. halococcitis was just 10, 20 years discovery, okay? We didn't know these guys would degrade, actually. And finally, we are hindcasting the past and setting hypotheses that simply cannot be refuted. We can say anything we want. We cannot get the data there, right? So it's a very subjective model, basically, okay? So there are inherent problems. It's nothing to do with the modelers, actually. So the question then is, philosophical question is, in a complex system like this, what do we do? Should we use a complex transport model to accurately reconstruct the past to such detail, actually? Or should we use simpler models to make really an approximation, very, very basic approximation, maybe an analytical solution, a mass balance, or even a professional judgment, okay? I mean, or some bucket type models, okay? Can we make some basic approximation which will guide the decision? Or should we use a complex model or a simple model? That's the dilemma. So in order to kind of think through this problem, I thought let's kind of reflect on a hypothetical problem. Let's say you have an industry which is leaking and there is a groundwater plume created by the industry. Well, the industry owner has no clue what's going on, right? So he is definitely panicking, okay? And he comes and hires you, okay? Now, what's the added value curve? So here's the hypothetical curve here. So when the guy doesn't invest any money, he has no benefit. He has no knowledge, literally, okay? So the curve here is what I call benefit factor, which is basically a knowledge gained, if you will, right? And then the money invested. So the first dollar he invested, you would come and say, you know what? The gradients are this way, so the plume is going that way. That's a very important information, because there might be a McDonald's here ready to sue him, okay? You can clearly say, hey, the gradients are pointing this way. Don't worry about the guy. Worry about your neighbor this way, right? And that's an incredible added value. You used a model. You used a Darcy's law there, right? And then he would say, well, you know what? I'm going to find the gradients, put a couple of L's and say, here's the rough velocity. So you don't have to worry. It's going to take probably another 20 years to reach that guy, and you can have some time to think about it. You don't have to panic now. Another incredible information, okay? So if we kind of build on that, as we start using, and you already added complexity to the problem. You're not only using Darcy's law, you're actually doing some field work and actually trying to quantify the velocity field, right? And which has got uncertainties and everything. But it's still unuseful. So similarly, you can kind of keep on adding some investment. My hypothesis is there exists a time beyond which the added value is very minimal, actually. It almost becomes flat, okay? Now, here's the kicker. If you throw in a lot of money and a lot of complexity, you invent so many parameters, you actually lose the problem. It becomes so fluid, you can pretty much justify anything you want after some time. Okay? So there is definitely a balance, basically, between a simple model and a complex model. We got to use some models, but where do you stop? I don't know that. This is just a philosophical part. I mean, but how do you do it for an actual problem? I don't know that. But at least it's a good idea for us as modelers to have this in the back of our mind, actually, at least so we know we cannot push too much. Okay? Now, despite that, people use two strategies, and what are the differences? What are the advantages? Well, in my opinion, when we do a simple conceptual type approach, which is what I call a geologist viewpoint, when geologists use all these drill cutting to come up with conceptual models, or even an engineering viewpoint. To me, Darcy's law is an engineering viewpoint. Okay? We don't know exactly what's going on. We said we looked at the gradient, we looked at the flow, there is a proportionality constant we call the hydraulic conductivity. In fact, that's exactly what Fourier did. If you look at the heat transport equation literature, go back, they were actually trying to figure out how the heat moves. Biot was the guy, actually, Laplace student, the associate, who tried to do all that. Finally, he gave up. Fourier basically came up with this engineering approach, which basically hypothesized heat flux is proportional to the gradient, and he slapped the constant, which is what Darcy did. So that's a good way to do it. But we lose something. A detailed mathematical approach, which is a physicist viewpoint, it's a reductionist model rooted in search of causation and fundamental principles. That's beautiful, actually. We know exactly what's going on. Okay? Now, the question is, which one is better? Well, the question itself, in my opinion, is a meaningless question. They are equally useful perspective of nature, yielding their own set of insights and approximation. It depends on where do you want to use the model, or what type of a question asking. For certain type of questions, you don't need the detail. For certain type of questions, you might need the detail. Okay? So you got to be very careful what question you're asking. Overall, if you were to take a decision, I always tell my students, I believe in this so-called kissing principle. Keep it simple, stupid, right? Yeah. As simple as you can keep. I mean, whatever you do, the elegancy comes from keeping things simple, which is the hardest part all the time. It's very easy to add terms to that. Okay? So with that, my concluding remarks for this talk is, I want to start with this little quote. Has anybody read this book, Useless Arithmetic? Okay. I think every modeling class should read this book, actually. This is Plinky and Jarvis are two researchers, ecology modelers out of Duke. And so when you get a chance, you should read. They got many examples, not just groundwater. They also pick on groundwater. And then they try to figure out why we do model and what are the pros and cons. And then in that book, there's this beautiful quote. There is a belief system is ingrained in the technology-loving American public. I would include that Western public in general, actually. That quantification is possible to any natural process. If we can't do it now, we will be able to. That's the we can attitude, right? With just a bit more research, okay? Just a bit more research. Now, he goes on and argues that this is a wonderful strategy because we as scientists did a fantastic job on public believing in that, okay? Why it's a win-win model? It's a win-win model because when we do this complex science for policy problems, politicians would look at it, and from a politician point of view, they can point out a research as action. Okay? When there is action needed, where is a policy decision to be made, or some other policy decision to be, like the Camp Lejeune, they can say we are funding the scientists, and they're studying. Okay? Before that, they run out of the time. Basically, there's the next election, they forget it. Okay? So it's a great idea for politicians. Now, scientists, of course, I get money, right? I get students, and I get to travel to Waterloo, have some lot of beer here. I should not put it on record, I suppose. So, so it's great. We do that. I mean, we can write some nice, great proposals, get funded. Our life is good. And the community group looks at it and feels that government is doing something, and the scientists are really working hard, which we do actually. Okay. So it's a beautiful win-win model, okay? And we are all happy in that sense, okay? Now, if you want to honestly look at it, so here are some quotes. So Lenny Konica is the guy who developed the first transport model, actually, okay? What is it, Mach, right? Yeah, it's a mod flow-based model, actually, right? Now, so he wrote a paper on transport modeling, and he kind of finally revealed his secret for successful transport modeling. And he simply said, the real secret is simply to lower the expectations. Okay, just lower the expectations. Okay, so what perhaps we should do when we write our proposal, which is very difficult, by the way, should be honest and lower others' expectation of complex models by openly acknowledging their limitations, especially when it comes to policy decision-making models, not scientific models. Those are completely different. Okay, perhaps we need a paradigm shift to view models as a computer-aided thinking or learning tools, or even a discussion tools rather than the prediction tools. Okay, computer codes are great for learning. Actually, when we do all these simulations, we can learn a lot from it. But the problem comes when you start prediction, and especially when you do hindcasting prediction, for which there is absolutely no data available, right? So with that kind of thinking, if you go back and revisit what happened in the Camp Lejeune project, clearly the ultimate goal of the Camp Lejeune modeling effort was to help decision makers, policy makers, this is Congress, US Congress, to draft a bill, okay, to address a healthcare problem. This is before the Obamacare, remember, we never had a healthcare bill until that. And it has to be a timely decision, because if you run out the clock, most of them will die actually, regardless of whether they had a health problem or not, okay, right? So you have to make a timely decision. It is not a research effort. This particular modeling effort is not a research effort, okay? So when dealing with complex social problems, modeling studies, in my opinion, can become an obstacle to action, because you just keep on saying, well, I need to do one more modeling, I need to do some more drilling, some more data, okay? You can do endless modeling. So we believe we should, in those cases, the modeling should either be abandoned completely or take a secondary role, where you basically advise politicians to make a policy decision, okay? And that's exactly what we did. This was one of the first National Academy studies which was critical about science, actually. If you look at the recommendations, we simply said further research cannot provide more definitive answers. Science is not going to solve your problem. We simply said that, actually. Now, that's a huge ramification. This is an NRC study, which means they ended up cutting a lot of funding, actually. Brown University was the part of it, Tufts was part of it, Georgia Tech was part of it. So a lot of people were mad, okay? So I remember after the study, I got a lot of nasty emails. So I emailed David, who's a National Academy member, and David said, you know what, if everybody hates you, then probably we did something useful, okay? Okay. So anyway, so we also said, in some cases, like epidemiology studies, stop or limit research and resolve this problem as a policy problem in a timely manner, okay? So that triggered a whole new set of debates, actually. And thankfully, there was a bill crafted, and that was drafted in 2010, and it took 2 years of political bickering between Senate and different committees, and then finally Obama signed the bill in 2012. And the bill clearly states the bill applies to 15 different ailments. And how did they pick the ailments? It's kind of eventually a political decision, actually, okay? There was no causation established, but they picked it, okay? And you can see the bill applies 15 ailments believed to be linked, because causation to contamination is incredibly hard to prove. A great example is tobacco. It took about 25 years for people to prove smoking tobacco causes cancer. How stupid it is, right? And right now there is a problem going on, which is NFL head injuries, right? When people tackle, they hit head on head. And so there is a paper already written saying that there is a causation. And you look into medical literature, there is equally other side says, no, it's not, industry funded research, okay? And I would speculate, it'll take another 10 years to resolve that. And of course there is causation, we know that, okay? To get that to the science, so eventually as a society, it's always some sort of a policy problem, okay? And model can be a tool. So the bill basically identified people and treated 15 ailments as part of the big bill, which provided health benefits to the people. So I want to close finally with one slide, which I got from George Andrews. Anybody knows George Andrews? Okay, here, okay. I didn't know about him too. He is the president of the Mathematical Society of America, okay? So he probably knows a little bit of mathematics. And I kind of accidentally came across him because my colleague is a Penn State grad, and he was retiring and throwing all the things from this thing. And I love when people retire, go and pick all their books and stuff, okay? So I picked up a little pamphlet put out by George Andrews. It's a local publication which had this quote. And before I go to this quote, and that same month he also came to give a distinguished lecture in Auburn, And I thought I'm a modeler, I know mathematics. I went to his talk. I did not understand even half of his slide. Okay, so I realized how pathetic I am when it comes to mathematics after listening to his talk. Now that guy says this: mathematics is not a mysterious substitute to educated common sense. When mathematics is abused, used in areas where measurements are extremely difficult and impossible, groundwater, especially heterogeneous groundwater system, it is at best a nuisance and at worst a trick to disguise ulterior motives. Okay, so we better be careful. So with that, I'll stop and be happy to take some questions. Thank you. So I got to talk about football a little bit, otherwise they'll fire me from my school, right? So. Yes, sir.
Donald Trump know about this. I think he would love it. I think it's only possible in that.
More questions?
Thanks for the nice talk, and generally I agree with your observations. And also, I have found enough papers from the famous WRR that are not correct at all, so I'm not surprised. So, I mean, on the other hand, as you said, that you can mix the limitations of morals and confuse the policymakers.
That's right.
Right? But one thing, I'm just coming from an engineering
Sure.
point of view, let's assume we're not worried about policy, we are just looking only at model and have fun with it. So I was looking at the data that you had, which is huge variance. One thing I don't normally see in groundwater literature, a clear indication of measurement errors.
There is, yeah, it's a great question. I mean, so basically he's talking about in groundwater literature, we don't emphasize too much on measurement error. I can give you my opinion, okay? Now, I was a consultant for 7 or 8 years, okay? First of all, people hate the word error, actually, okay? So the minute you say error, they think you made a mistake, something, right? And the problem with groundwater is, when you say it's a measurement error, it's really not a measurement error. That's actually, those numbers are absolutely good, actually, okay? The error comes because, well, that's what they measured. The measurements are fine. I mean, we went to a solid GC protocol and measured it. The variation comes from, variation is in the problem, actually. You have different stresses, strains, and all kinds of variabilities. Sure, yeah. Okay, so it's a natural variability which gives, it's inherently a stochastic problem, essentially. And so a single point measurement has absolutely no meaning, actually. And so what is really needed is probably a multiple measurements and some sort of a trend. I mean, can we extract some trends from it? And now stochastic hydrology is probably a field which tried to explore it, and they got their own limitations, actually. Okay, but it's just it's inherently a fairly complicated problem, actually. And that's one of the reasons, as I said, all my lab work, I just don't deal with heterogeneities because I just gave up on it, essentially. And I would rather, as an academic, just look at the idealistic problem and go after the theory. I mean, Darcy's law, very fundamental problems, because field situations are really complicated. I mean, it's just a natural variation. Like stress, a simple thing as simple as sources, as I said, right? We don't know the idea of sources. So what sources we should put in the model? We make all kinds of guesses. And pumping, we have no record of when the pump stopped, when in 1955. We don't have that record, right? So you come up with some guesses. And those things throw things off, basically.
Sorry, just at the same point, I don't want to take
sure,
all the
that's
time.
fine, yeah.
Because generally coming from a traditional engineering
sure, yeah.
viewpoint, we would consider, I don't know how they took the data, and I don't even know if you know it, because generally when we take data, we always look at many samples of the same thing. So that gives you some idea of already variation, but I don't see those kind of things because the money problem.
Yeah, right? It's a money problem. And this particular site, that data I showed you is what actually collected in 1985, okay? And the whole idea of measuring PCE in groundwater was just evolving. So it's very expensive measurement, actually. So the money is one of those things. Although I would argue that even if you threw in a lot of money, I don't think it's going to make a huge difference, actually, unless you have the stresses in the system.
Yeah, that's always there.
Yeah. Now, on the other hand, I listen to lectures in my department, structures faculty. My department chair is a big reliability bridge guy, and they do a very interesting approach to the whole thing. But the thing is, they can control everything, The bridge is outside. They can measure it. They can see things going. But for us, everything is hidden, right? So that makes things difficult. But on the other hand, we can say anything we want and get away with it. So.
Hey, Prabhakar, very interesting talk. Really enjoyed it. I had two questions. One was kind of a more philosophical question, and the other was, so the first one, which is related more to the data. So there was a lot of variation in the data over it
very
seemed
short
like
time, yeah.
Very
like
short time.
Yeah,
So
couple of months or something.
Right, and you mentioned that this was near the source area.
Very
so
close.
was that because of free phase in the water rather than dissolved plume?
Yeah, it very well could have been. So the model they used was a ModFlow based model. So MT3 was the solute transport model, and then they used modules of RT3D for doing the reactive transport. I mean, ModFlow cannot do any multi-phase flow, right? So they come up with some approximation to inject mass into the system, actually. Right. Dry mass injection, they call, right? To create the source. So yeah, that could very well be an artifact of that, and in reality, actually. In reality. Yeah.
So my other more broader question was, so looking at that data and that model, in hindsight, would you say that there wasn't any need for model because you could average those 5 points, and the average you could put it back in time, and that would give you the exposure?
Not really, because that data was only for 1984, right? What they want is all these people lived in. So by 84, they actually had an alternate water supply, actually.
Right, okay. But if I look at that plot, it's more like a flat line, and then there's the sharp rise, making the assumption that you're dumping the DNAPL at one point in time, whereas in a typical dry cleaning operation, it's dumped over time, right? I would
That's
think
right.
It's not a single point
exactly.
injection.
So what they do is every batch they do it, they just dump it in the subsurface. So yeah, I mean, you could, every time you did that, you can take an average. Yeah, you could probably do something like that. And that would be equally valid than spending so much. I mean, you're talking about several millions on this modeling effort invested. Or I would say invest more on field work, actually. They could have done and made some more drilling and found what's going on, and somehow use intuition and professional judgment to come up with a decision rather than doing this complex model.
Right. Thank you.
Yeah, DNAPLs, definitely. Yeah.
Yeah, perhaps just a comment. I mean, I agree with the concept that keep models simpler and no simpler, which is something Einstein said many years ago.
It's easy for Einstein, though. So
yeah. But you know, depending on whether you choose a parsimonious model versus very sophisticated rather than complex model, I guess depends on the questions being addressed. There is always lack of data. I would say over the last 30 or so years, we've gotten better.
Absolutely.
In accommodating, filling in for data, subsurface heterogeneity. We've learned a lot in the last 30 or almost 40 years now. I've worked with Lynn Gehar and Gideon and all these guys. But it seems to me part of the problem is, and Emil Friend might agree with me, he was my advisor, that in the higher educational system, the training of, quote, modelers, maybe we should call them analysts, is starting to wane in ways that they're not necessarily trained to understand processes, as well as not just fill in a menu and hit the return button. I mean, the modeling is much more than that.
Yeah,
to understand uncertainties in the input.
Yeah.
How does that potentially propagate to uncertainty in the output? And oftentimes we're seeing that, my former student here might agree with me, in practice, you know, you have a student who comes out from undergraduate, he's told, you got to model this situation. Maybe master's or PhD, they really haven't had that depth, including even the numerics underneath.
Sure, yeah.
So it's becoming almost a lost resource. There's not so much training in this field, in this area anymore. So it's kind of we're at almost a crossroads now.
Yeah, yeah, it's
kind of like, okay, we understand quite a lot now, but are we really properly training the people that use the models, apply them, to do it in a proper way at the proper level with the proper
Absolutely.
understanding.
Yeah, yeah,
So
yeah.
it's kind of a comment.
Yeah, well, yeah, it's an excellent. I mean, I personally struggle with that. I can tell you that because I was trained in the old school. I was Fred Moll's student who came out of Remsen's lab. Yeah, and he debated with stochastic guys a lot actually. So and so Fred, I mean, Mott flow was already there. I went to school between '88 to '93 with Fred actually, and so I actually talked to him about Mott flow a little bit. He would never liked these models, and so he would derive everything. I mean, every time you start with the mass balance, you derive the Gowning equation, and then you numerically solve finite difference. We go to an old VAX computer and type the green letters and write a program actually, and that's that. Now, so I got a good friend who's a GMS developer, Norm Jones at BYU. So he teaches a groundwater class. I teach it completely differently. So now Norm's perspective is, why bother them with all the little details when there is sufficient to grapple with all these conceptual thinking? So I actually think, I mean, now I come from this bottom line approach actually, but I think there is room for both. If you are a master's student, want to live in the professional world to provide some policy models and rough models, maybe that's not a bad idea. Give them the basic equations a little bit, but let them do different case studies. There's so much to be learned. I look at some of Norm's notes. It's really interesting actually. He takes a real problem and thinks in terms of boundary conditions and stresses and all that stuff. Whereas I think in terms of the governing equations and discretization and all. He never bothers with that at all actually. So maybe it's an evolutionary process. I'm just an old guy. Just.
Well, it's got to be a blend. I mean, here.
But there is no time, right? I mean, you can't do both. I tried to do that.
We've always had a tradition in certain courses. I mean, you had to understand processes. You know, the fundamentals of theory of flow through porous media, transport, reactions, these kinds of fundamentals, and then Emil and subsequent Andre Left followed up teaching advanced. How do you represent these things mathematically? But also limitations of models.
Sure, absolutely. That's
some
the big
people,
thing,
managers might think a model is perfect. They're far from perfect. They're just a representation of what we know and nothing better.
Yeah. So maybe with time you should evolve into, I mean, academics to evolve into two groups probably. I mean,
it should be harmonized. I think we can't have a mathematician
one side and
group
that
of
is probably true
modelers
too,
and then a process understanding hydrogeologist, hydrologist side, because eventually they don't talk.
That's true.
And you end up with bifurcation of ideas and you know,
but some programs,
retrogressive.
So I teach in a civil program basically, right? I get one class where I got to teach groundwater hydrology, contaminant transport, and some applied modeling.
Well, that's why I'm saying it's a little bit of an obligation at the academic educational level to figure out a way to not lose this
the fundamental
full-bodied education, let's call it.
That's right. Yeah. That's true. Yeah.
It's so complicated now. Well, it's complicated, but it's 2016 and we're a lot smarter.
I'm not sure about that. Yeah, I need to test that hypothesis. I'm not sure we are smarter.
I think we are.
Well, I was talking to, this afternoon I remember Fred telling me his WRR papers, he only wrote 3 versions. He would write one and his secretary will type it up and then he'll edit it and then he'll edit over that, type it, submit to WRR. Those papers were precious compared to the papers we write now.
I mean, to say we're smarter now, and we know better or should know better what we can't do, and be honest about it.
Yeah.
One more question. Yeah, I have a question about your conclusions. Should we live happy, depressed, happy to be depressed, happy to be depressed, or depressed to be happy?
I think we should be happy to be depressed. There's nothing wrong in that, actually. I mean, some amount of humility, basically. I mean, it's easy to be carried away that we can do sophisticated science when we realize there is more to this whole sophistication. And the big thing which bothered me serving on the committee was here are some really brilliant, outstanding biological researchers, medical doctors. They really give a lot of value to engineers and quantitative people, actually. They think that we know everything, okay? And we should be a little bit careful exploiting that. We almost done a good job of marketing ourselves. So in that sense, it'll be nice to be kind of a self-reflective a little bit. So.
Very nice. Any other question?
Just sort of final, more like a comment, is that you did show a little bit of uncertainty in one of your, the main slide. Yeah. So I don't know where that came from. But
they did a Monte Carlo simulation.
Yeah, but see, again, it's like what you said. If you don't have the proper, first of all, proper idea of how this uncertainty came in, it could be from parameters, could be from sources, whatever.
Or from the model itself. I mean, how do you conceptualize the model?
It could be any number of things. But if there is a way to quantify, I don't think it's that easy in groundwater, but it's, at least you should at least try, like you said, and then give, okay, this is my assumption of uncertainty, because there's no way you can prove or disprove this, and this is what the results you can get.
Sure.
Right? I'm almost sure that, I don't know how much of the variance it can explain, but definitely it can do better than I think what they've done.
Probably,
And also, this is because most of the people, like almost all of us on Earth, I think we are deterministic-minded people. So this is something you have to go beyond your mind.
Absolutely.
And most modelers are not good at it.
Yeah. And also, you should report it. See, when they actually put the data on the web, I don't think you should have put 152.55. They should have put 152.55 plus or minus 50. which means when you round it up, it should be 100 plus or minus 50, something like that.
I agree with you. We are smart enough. If you go to a waiting time, the emergency waiting time in the hospital, they actually put
how much
90% chance of, average time is 2 hours, the 90% is 7 hours,
yeah.
right? So they're smarter now.
Okay, more questions?
So I was wondering why you took I thought towards the end, you took a little bit of an all or nothing approach, because it seems to me that don't you care about starting off backwards, saying what is the kinds of things which would make me change my mind? So in the sense, your final conclusion was you have a bunch of people sit around the table, they're just going to randomly pick a list of diseases, and then they're just going to fund those people who have those diseases, right? But is there anything that...
No. Yeah, go ahead.
Is that not right?
No, it's not. Okay.
There's something more sophisticated than because you said it's a political process and they just picked some.
No.
So then it seemed to me that what you might, an in-between approach would be that you might ask, what are the few things that might actually shift from my making this decision to that decision? So if you start off with a set of final policy outcomes and concretize them and then say, what would it take me to know if I had to move from here to there? Maybe then you can come up with some bounds or answer.
Absolutely.
And maybe that's what you did. I didn't get.
Well, so in this case, it's not a bunch of people. These are like Harvard and Yale medical doctors and epidemiologists. So the thing was, we basically shifted the problem to their hand. I was basically saying that, hey, you guys have all this information. As a groundwater modeler, I'm not going to provide at the level of detail you think you need. You simply cannot. This is the best we can do. Okay. Therefore, they did all kinds of epidemiology investigations and stuff, and they used their professional judgment and they recommended those diseases. It's not totally. Now I've been privy to some other discussions, and some of the diseases were kind of a compromise. There would be a huge argument actually between two epidemiologists how to look at the data. It's fascinating actually, and also they have factions. I didn't even know there are two fields called epidemiologists and toxicologists, and they don't like each other. They hate each other actually, and because one guy deals with the rats and stuff and to find the exposures, the other person looks at the actual human population, and they kind of completely disagree with each other's positions. So there is so much uncertainty. It's just like anything else, the tobacco thing I pointed out, right? So it was now what we accomplished as a committee was, if we would have not come back and basically acknowledge this thing, the proposal was to do a more complicated model, which is we use multi-phase flow to reconstruct the DNAPL movement, and then some mass transfer model to find how this will time variant, some really sophisticated modeling. And we said that is great research. That's not going to solve your problem. It'll give you 10 more WRR papers, completely worthless for these people who are dying. And so you address this somehow. And so in that sense, it's a political compromise, but it's a very educated political compromise.
Okay, I propose we close down here. Thank you very much,
All right.
Dr. Clement, once again.
Thanks for the opportunity.